Hi, everyone. My name is Jackie Kate, for those of you who don't know me. I'm a software engineer at a small stealth robotics startup called Marble. For the past 2 years, though, I worked at a company called the Open Source Robotics Foundation. It's a very descriptive name. I used to make open source software tools for robotics, including ROS, which is an open source networking framework, and Gazebo, which is a physics simulator for testing robotics algorithms before deploying them on a real robot. So one goal of that organization is making tools that are accessible, and accessibility also involves cross-platform compatibility, which is not something that those tools previously really succeeded at. So what I'm going to talk about today is some lessons I learned from looking at implementing a cross-platform version of the RTPS wire protocol with a partial implementation of DDS. I'm going to get into what exactly those are because this industry is full of acronyms that don't really sound like anything in a little bit. But again, we're going to kind of do some high-level stuff here and talk about one of the many problems in robotics, which is communication. Communication is really hard. And you might not know this, but when dealing with robotics, there's a lot of computers involved, and not just the computers that are on board the robot. And yes, there are multiple computers on board the robot. You're going to start out writing your code on your developer environment. Your laptop might be a MacBook Pro, whatever. It might be a ThinkPad running Linux like me. You're going to compile it. You might cross-compile it for a target, for an embedded target, or you might compile it for an ABI-compatible Linux machine, depending on what you're going to run on the robot. You might also talk to a cloud server that stores offline data. And the cloud server might also talk to the robot, taking data or sending commands via a teleoperation interface. So this is kind of important, this 3-node communication, 3 or more, really, because you might have more robots talking to each other. And as I hinted to before, you're going to have a lot of computers on the robot of different classes. Those computers have a lot of different roles. Really, what a robot is an intelligent interface to sensors and actuators. That's anyway how I conceptualize it. And a sensor is taking in analog data from an analog circuit and then translating that into some digital representation. And a microcontroller is doing the reverse operation of translating from information from a digital interface to an analog representation. So why am I getting at it? Why is this important? And how is this relevant to what you came here to talk about? Well, there's a lot of embedded systems, and a robot is going to include, maybe a couple of these. And what these are different classes of embedded systems. And I wanted to we don't have to get into all the details, but I wanted to throw up some numbers to give you an idea of the diversity and the spectrum of computational power that we see these days. So when you think of an embedded system, you might just think of a computer without a screen. I find this not a very useful definition because there are computers without screens that are as powerful or more powerful than the laptop you might be using right now during my presentation. For example, the Intel NUC is a small form factor Intel x86 RISC whatever device with 16 gigs of RAM. And when you compare that to the bottom class on this table, the MSP430, which I actually changed this slide after Jason's talk. I wanted to call it the MSP430 because he gave it as an example of something that's roughly computationally equivalent to the Commodore 64. And that's the kind of device that we'd use in a wireless sensor network when you need a really low-power device that might spend most of its time sleeping and then collecting data and then reporting that data back to a central server. So anyway, we're going to focus on one of these classes today, and it'll be this one. So that's this. I think of this as maybe you have an MCU that has to talk to a camera or some non-trivial sensor, and then there's a driver that then relays that information to a central core processing unit on a robot. So this is just kind of filling out some details. You have operating systems. You have Tux and you have the Apple, whatever. I prefer the Penguin over here too, but each to their own. And we're going to focus on, as I said before, the classes that will be associated with sensors and motor controllers. So I think this outline slide is like really common at CppCon. Again, this was in Jason's talk, but just with fewer details. And I swear I made this before I saw his talk. This is roughly, the layout of your computer. There's the CPU, there's a memory, and that's connected to the bus, and the bus is connected to peripherals. And your operating system serves between the CPU, the bus, and the peripherals. And it provides really nice things that make coding a lot easier. It's going to manage your processes and threads, your control flow. It's going to allocate memory from the heap to different processes. And it'll provide a unified interface for things like your monitor and your keyboard, your Ethernet, whatever, things you interact with a lot. And when people refer to bare metal development, they're talking about not having any of that. It's what we saw in Jason's plenary keynote. Technically plenary. When you want to access these peripherals, you're just directly setting values in registers. There's no abstraction. So I think in the abstract I mentioned bare metal development. The abstract of this talk did drift a little. We are going to talk about working with an RTOS today, or real-time operating system. I prefer to say RTOS. RTOS is like way too much of a mouthful. So a real-time operating system is I like to think of it as a small operating system with components that you can grab and put into your embedded binary as you pick and choose. It is I'm graphically representing it as a thin layer of operating system that you can put on your device. And what's cool about embedded development is because you're cross-compiling for a small target. Unlike when you're doing desktop development, when you compile a binary and then when you execute the binary, that gets loaded into memory. When you compile for embedded, you're actually flashing the device, the computer, with the startup code and the kind of the sole program that's going to run. So it's kind of like you're compiling your own operating system, but like everything too. So most real-time operating systems, you can select some kind of subcomponent of operating system functionality that you need for your specific application. And I'm explaining that because I'm going to show you just a really quick size comparison to show how thin a layer of real-time operating system we're going to use rather than using Linux. So we're going to use the size command. Size is a Unix command that gives you the size of a binary. And it gives you 3 outputs. The text is the instruction tape, essentially, of assembly instructions that you're going to use. Data is the, see if I get this right, the initialized before runtime variables in your program. And BSS is the area of memory dedicated to uninitialized variables, stack allocated variables. I'm going to compare, we're comparing here the size of the Linux kernel to a test binary. The test binary is essentially using most of the threading capabilities of FreeRTOS, which is a particular real-time operating system that we're going to use today. And the takeaway here is that it's literally an order of magnitude lower than the Linux kernel. And that's important because of the tiny sizes of things on this previous slide. Okay. So, and just to keep things really kind of specific, when it's relevant to talk about specific hardware and a specific RTOS today, we're going to talk about, CMSIS or CMSIS wrapping FreeRTOS on the ARM Cortex-M7, and just like to expand that out, that's this wrapper around different real-time operating systems that ARM made up for the Cortex-M family. And as I said before, we're going to focus on that class because it's useful for robotics. So now we're going to actually talk about how we're going to design a library using modern C++ to implement this particular networking protocol. But I'm going to kind of shy away from talking about the specifics of RTPS and DDS today. In case you're really curious about learning more about that, I can just find me afterwards and I'll tell you more about it and give you some resources. But I think it's more interesting for this audience to talk about C++ specific problems. So this is an overview of what you might get, an incomplete set of what you might get if you use C++ rather than C when you do embedded development. And the reason, I sort of vaguely ordered this so that things that are considered somewhat harmful are on the right. And you've probably heard a lot of reasons why these things are considered harmful, because they incur a cost that you might not have asked for, right? And that's what we're really concerned about, is incurring a cost of something that's not in our control. STL containers, you can choose not to use those, and the reason they might be considered harmful is because of dynamic memory allocation. But exceptions in RTTI, if you don't turn RTTI off, you're going to get a cost for it whenever you have classes or types in your program. So we have some tricks. We have some compiler tricks for reducing code size so that the size of your compiled binary can fit on this relatively small space. The first two, I think, are self-explanatory. Then they're some maybe one that I had no idea about until I started putting together these slides, actually, is short enums, which chooses the, for enums where you don't specify the underlying type, it chooses the smallest underlying integer type for enum storage. And then there's this kind of catch-all compiler flag you can pass. I think these will work with both GCC and Clang. Yeah, I only use one of those. So OS is maybe you didn't know about this. It's rather than optimize for speed, optimize for space, because that trade-off can actually be that can be a trade-off between those two. So unlike maybe game development, we're not going to be optimizing for speed. Keep that in mind. And so I mentioned dynamic memory allocation. I just wanted to, we're not going to go over all the details of how you set up your embedded toolchain today, because there's a lot of much better resources online that you read about and sit down with and kind of tear your hair out over. But I wanted to give you guys a taste of the fun that's involved in doing things like modifying your own linker script and modifying vector interrupt tables. So one thing that's cool is so whenever you interact with a C++ program, or when you compile one and you interact with the linker, you probably aren't writing your own linker script. But if you want to set a specific heap size and stack size, then you may want to probably modify an existing linker script that's suitable for your instruction format. So this is an example of how you would use the linker script syntax to do that. These are variables that are set somewhere higher up in the linker script. And you also, it's probably very rare that on desktop computing, that you're going to modify vector interrupt tables. But in case you wanted to do that, here's an example of some assembly you can write to load registers into memory to, again, limit the heap memory and stack memory used by your binary. So now that we have some tooling out of the way, let's talk about actually some C++ code you can write and patterns employed in this particular domain that I was interested in covering in this project that I overtook. Yes. So at the very core of it, the design of a networking library, I think, is serialization, dealing with concurrency and sockets. And this is a very simplified view of what might happen. You have an in-memory representation of a struct, of a message that you want to send. And then you serialize it to some byte format that is agreed upon by the two endpoints of communication. And then you have some function that stuffs that serialized byte stream into a socket. And then that socket does some magic over the internet or whatever networking protocol you're using and sends it to another socket, which was previously configured to discover the sending socket. And in this thread of execution, this process represented by this block has been sleeping, or whatever it's been doing. It's been waiting for a packet to receive. It deserializes the byte stream contained in that packet, and then gives the process on the other end some nice in-memory struct representation of that message. So DDS stands for Data Distribution Service. It is a distributed networking protocol, which means that there's some extra stuff on top of this to enable nodes to discover each other on the network, rather than something like MQTT, where you'd have a central broker that basically all nodes are configured to listen to for network information. So rather than having a central broker, all the nodes talk to each other, and it's kind of messy, and you get this weird mustache pattern. I don't know how that happened. So we're going to ignore those details in today's talk, because they're kind of out of scope, and talk about really common patterns that might be more useful to anyone who's implementing not just a networking library, but serialization happens all over the place. That's what I'm trying to say here. So here's kind of an old school way of doing this. You have classes, and naturally classes have a serialized and deserialized message. And maybe these serialized and deserialized messages look really similar. So what a lot of people like to do is have a code generator, and this code generator takes some agreed upon IDL format, IDL standing for Interface Definition Language, and maybe it uses some other language or to generate C++ sources that have an agreed upon API design, and maybe they inherit from some generated message superclass that provides some functionality. I really like audience participation. I should have started doing this earlier. Who here has worked in a code base with code generation? Okay, so who has worked in a code base with code generation that's not, I can see how someone would twist this, that's not generated by the compiler. Okay, cool. Just to get that out of the way. So I skipped ahead a little bit there. There's a way of doing code generation in C++, and I'm going to try to show that it's pretty simple and can be done really, really easily with existing libraries. And the idea here is that you define a serializable concept, and you provide template functions that describe how to serialize kind of the primitive types of your serialization strategy. And then you basically use metaprogramming to iterate over the fields of a struct and serialize those subfields of your serializable message. And then you do the same operation on the other end with deserialize as you read bytes out from the byte stream. So this I don't have syntax highlighting on these slides. And this is also complete pseudocode. This is not syntactically correct at all. This get fields of thing, it looks weird. So I'm going to show some real code here, and it might be too small. So to give you a point, I am going to present some benchmarks, and I'm going to use an existing, well-established serialization library, which is the Google protobuf library, which was, I don't know much about its history, but I think it was designed pre-11. JF is nodding. He used to work there, so maybe can I trust you? I don't know. So this is an example of some of the header that Google protobuf will generate. And I actually realized I should show. Didn't have this ready in my. Okay, so I'll show the IDL that you provided to generate this. It has this external format. I've defined some fields that are very creatively named, and then it generates 400 lines of code to do some operations on it. And this is, I'm scrolling through it very fast, I'm sorry, but I just kind of want to give a point that it has generated a lot of code. This is the first approach that I mentioned of code generation. The second approach this is kind of one way you could implement it using two existing libraries. Basically, we're going to use Boost HANA for limited type introspection and providing what we're going to kind of co-opt as the serializable struct, which is not going to be represented using proper concepts. Sorry, guys. And we're going to use a library called Serial, which is a C++11 successor to Boost Serialization, which kind of has its own problems that I'll get into more later in the talk. So what I like about this class is that it's kind of like its own IDL and its own in-memory representation, or a C++ native representation of the type. So you don't have to have this type definition redundancy that exists in this other style. What I also like about this is that because it's C++ native, you can do things. You can define your own kind of interface to this struct while still conforming to the serializable concept that we mentioned. It might be a little bit out there, but what I'm trying to say is if you make a more complicated message type and you have template parameters to it, then you can understand things about the message through its template parameters that a Google protobuf type will not have because it was constrained by this code generator that someone else designed. Again, we're using externally defined libraries that we didn't make here, but we have a little bit more freedom. OK, so for anyone who's confused about this syntax, I'm using a macro that's defined in this other library, HANA, that essentially makes this message or this struct iterable. Is this too small? Can people see it? OK. It makes this struct iterable over its fields. And you can actually define it externally. So you can call a different macro on the struct on like a normal looking struct. Which I think is cool because that means you could then externally make a class someone else defined conform to my serializable concept. OK, so that's how you define the IDL for this scheme. And this is how you implement serialization over types that conform to what we're calling our serializable concept. Really here, again, I'm stealing the HANA struct concept. And that is this thing here. Basically, I'm saying only enable this function for this template specialization for my serializable struct. What we're doing here is we're providing load and save functions to Serial, our serialization library, to guide it to know how to archive our structs into a serializable, byte serialized format. We're invoking this kind of like static for each over the fields of our struct, and it's kind of silly because Serial actually already understands how to serialize pod types or plain old data structures. So it doesn't know how to serialize what's essentially a tuple, which is like a list of types, which is what we've turned our struct definition into. So what we need to do is tell it how to iterate over those fields. And then it actually then knows how to serialize the rest of our message. And we do, for the inverse operation of load, which is essentially deserialize our message from a byte stream. And you'll notice here that the type of the archive, which is what you can think of as the object that's saving our serialized byte stream, or our serialized bytes, not the stream. So load is basically taking, it's doing the inverse operation of accessing into the kind of map-like structure of our HANA struct. And I want to point out that this is a really small file. I didn't need to write a lot of code, and this my serialization system can now serialize and deserialize any struct that is that conforms to this concept. Let's see. Okay, yeah. So I think that was like a lot of metaprogramming, and I glossed over a lot of the details. So for anyone who is not familiar with these kinds of libraries, you should definitely check out HANA or MPL is the kind of pre-11 way we did this. I wanted to show you a benchmark over some various file types using these two different styles, because I guess I think it's common that people don't use this kind of metaprogramming on embedded. So and I wanted to just show that it can indeed fit in this really limited space we have for code size, and it actually does like a lot better for these particular message types than the code generation example.
These are bytes.
Yeah. So yes, it's always going to be in bytes. This is order of kilobytes for all of these benchmarks, and the benchmarks are really just at this point saying, instantiate my type, stuff some fake data into it, and deserialize it with some extra stuff to make sure that the result of deserialization doesn't get optimized out by the compiler, because that would make for a really lame benchmark. So that's the actual process of stuffing your user-defined. When I say user, I mean user of the library, user-defined types. There's another kind of tricky thing here, which is that when you are getting a packet off of a socket, you don't know what type you're going to get. You do know, but it's in the header of the packet usually, and it's there's some clear mapping. But the point is that you don't know what type you're going to get at compile time. You have to do something to get the right type at runtime, and the reason this is might be ugh, for some people is that I think people would probably immediately think you have to dynamically allocate something in order to make this happen. Drink some water. Sorry. So this is again some pseudocode saying what we need to do is we need to fill in this magic comment, because I want to stack allocate my message that is coming out of my socket that produced some binary blob from a socket, and I want to deserialize it and stuff from the stack allocated message, the data that was gone from the socket. I want to execute a callback. I want to execute some behavior that operates on that message that we got on the other end. So this is one way of doing it. Basically, it's very straightforward. There's some stuff missing here, but take the star quotes, the commented out line here, replace it with this. You switch on the header. You translate whatever you got in the packet to an enum type or some identifier. You deserialize it, and then you have a callback. And this will work pretty well if there's no arguments that you have to return out, or no result that you have to return out of the callback. And this is really straightforward, because you have a function, the type is known, the result of your deserialization is known, whatever. But this isn't very scalable. And the reason that this isn't generic is, and the reason I'm concerned about that is because I used to work on a middleware where we would provide users with this library, and then they would plug in their own types. And they can't just modify this critical section in the library with their own switch statement, obviously. So we need some kind of callback registration. And here's another pretty naive way of doing it, is you have some callback map type, and it's stored somewhere. Maybe it's global, or maybe it's passed around to the socket deserialization thread. And then the user has this function pointer, or the user provides a function pointer to the map based on some identifier. And we've switched from using enums to strings here because it was kind of lazy. So you then when you reach, you have to identify in the packet structure that you have a user-defined type. And then when you're in your switch statement, you have to say, all right, I'm going to look up in my callback map what the function was and call it. And a huge disadvantage of this approach is that the user has to basically provide some deserialization mechanism if they're using this pattern. And they have to call deserialize themselves. They're providing the type of the thing they're deserializing here, which is kind of nice because we can still stack allocate the message. But there's a lot of room for error. It's not type constrained. And that kind of bothers me. So I was like, I really like metaprogramming. This is fun. So can we make something that's more generic and that works kind of well? So I thought a little bit about it. Another really cool tool that everyone should use is a compile time map. So I thought, we can like match the types of these messages to a callback and then call the callback, whatever. It's going to be great. There's a disadvantage of this and we'll get more into the code. There's a disadvantage of this approach that you can't define the callback map that registers our callbacks in a separate translation unit from where the user will register the callbacks. And the user will probably register the callbacks in the main function, or in their own user-provided library. But I actually decided this was totally fine because when you do embedded development, you need to statically compile everything into one binary. So maybe it's okay if we provide the user with tools that are all are header only. So this is probably not very clear. So we'll do another code example. How am I doing on time? Oh my gosh, okay. So let's see. This is one implementation of the non-generic approach I described, where, let's see. Yeah, it's very straightforward. It's almost literally what I wrote on the slide. This is some attempt to implement the compile time or the metaprogramming approach of what I described. So we have some map structure that we can iterate through, so we store the types of the messages we're going to deserialize and map them to functions that the user can register. And then we search through that map. We have to match the type keys of that map to runtime values, which are the string identifiers or the encoded identifiers for the message type that we decode. So the user has to provide the type of the thing they're deserializing, the identifier to match it to, which is probably going to be defined by our protocol, and the callback. And so what we do is we store those in a compile time map, and we also store a sequence which matches a runtime string identifier to a type, and that type is actually a type value as defined by our metaprogramming library. And we do something that is like, kind of questionable, which is a linear search through the map when we receive the packet on deserialization. And that's so that we can then match the header of our packet to the correct type. So this is it's fun to write. This is some syntactic sugar to build up the callback map. And what it looks like in the wild is like a really nice API. Imagine the user is registering their various callbacks, and they can basically pass in a lambda, and then they can bind anything they want to the lambda. This is a benchmark, so I'm doing like some naive thing to make sure that the input to our deserialization callback doesn't get optimized out. And then because I want to write fewer lines of code, I decided, and I happen to have the latest and greatest Clang compiled on my computer. We're using destructuring C++17 structured bindings here, if anyone's not familiar with that syntax yet. So this looks really nice, and this is like maybe preferable to this other approach I came up with, which is probably very low overhead, but has more room for error on the part of the user who writes these callbacks that are provided to a map. Unfortunately, things didn't go so well when I actually benchmarked it. So thank God I benchmarked it. And again, this is a like back of the envelope calculation. The number, I wanted to see how it scaled in the number of callbacks, and I didn't go up to like 100 callbacks. Realistically, I think in a library like this, you would expect like around 20 callbacks. But the generic approach that involves a compile time map, it actually ends up not scaling as well as this what I call static callback approach. So that's like a valuable lesson. At the very least, I think the lesson to be learned here is you should just benchmark things. And it's really obvious, but I think there can be a culture of I am going to write something that I think will work really well, and like pushing a lot of logic to compile time obviously means things will run faster. But that's or compile down to a smaller code binary size, which is our goal here. And the other caveat here is that I was using this library serial to implement serialization that works really well, and it can actually be extended to other serialization types. So by default, it uses its own binary encoding, but you can write your own stuff to serialize to XML and JSON, or your own encoding, which is what I do if I'm implementing a networking library. What I actually ended up doing is basically writing my own CDR, which is the RTPS spec serialization format, another acronym. I wrote my own CDR deserialization format for this because Serial uses both RTTI and exceptions. It uses exceptions just as an error handling mechanism, and it uses RTTI to as a part of its, I believe it's as a part of its encoding function. So as kind of like as a type identifier, because that's what RTTI is. And so it's really not going to scale well to small embedded devices, but it's a really nice interface and a nice paradigm because of what I showed you with you can externally define serialization mechanisms for structs, and I think that is it's either there's a library that is open source and nice like that is it might exist, but I'm not aware of it. If anyone is, then please raise your hand and mention it now. Okay. So that kind of covers part one of what I mentioned, or it's a taste of what I mentioned goes into implementing a networking library. Sockets and threads is a kind of a lot of stuff, a lot more acronyms. So this is comparing how different operating systems are going to manage threading standards and sockets. Because actually, well, POSIX generally refers to pthreads, and on Linux you might have Berkeley sockets, whatever. And the interfaces to sockets and threads are going to be different on different operating systems. In the ARM world, which is what, in the ARM no OS world, which is what we're talking about today, there is, as I mentioned before, this abstraction layer between different real-time operating systems, and those different real-time operating systems provide threading abstractions. And there's also an interface to this library called Lightweight IP, which I've pronounced in my head LWIP every time. Sounds kind of weird. And you know, this is like kind of another abstraction layer for nice operating systems, things that we want. But unfortunately, there's not all of the things that we want are accessible, and that's why embedded programming is hard, right? So we have some nice ways of dealing with concurrency and threading in the desktop computing world, which include standard thread, which we all probably really appreciated when 11 came out, and then this library called ASIO, which is the kind of the de facto standard, or the proposed standard for for C++, and the design of ASIO is going into the networking TS. So unfortunately, the C++ standard library provided by ARM does not include thread. In fact, this is a direct quote from their user manual, which is great. And this makes sense if you think about it. They don't want to impose an RTOS implementation on users of the ARM C++ standard library for embedded no OS systems, because the operating systems abstractions are like a choice that you compile into your binary. And also, as a point, threading and concurrency is built into the architecture of ASIO. It basically, I'm not a developer on ASIO, but I've looked a little at the source code, and they're basically wrappers for different platforms, for Windows and for POSIX. And before 11, they had their own threading abstraction, and the only requirement, which seems like a very permissive requirement, is that you need to implement thread join when you're blocking on another thread for it to finish execution. So I thought, okay, a fun example to show people. So wrapping sockets is like, yeah, that's probably just mostly API wrapping, not so interesting. But how hard is it to compare the concurrency primitives provided to us in this abstraction layer with that abstraction layer, which is a dependency of this abstraction layer, so that we can just like throw in ASIO and standard thread and have super cross-platform clean C++ code. So that's the point I just made. And this is going to be another code example. And I drink water. How's this font size? Maybe better. Okay. There we go. So the CMSys interface to concurrency primitives gives us signals, threads, mutexes, event queues, some kind of nice stuff. And the way the API works is through these things that look like functions but are actually macros. This OS thread def thing Yeah, so it's actually a macro, and I was confused by that initially because it's not in all uppercase, so some people like to do it. But it defines another function using the name of the function pointer that you pass to it, which was like not the most intuitive API at first. So I decided to wrap that in something that would look a bit nicer, which is a thread that uses RAII to take a function and run. Okay, thanks. Run and then manage signal handling so that any threads that are blocking on it can block accordingly and then clean up accordingly based on the necessary calls that are needed by the RTOS to signal to the kernel that it's done. So this is a pretty standard and short way of doing this. There's, let's see, you can kind of step through initialization. I didn't make this default constructible. What you could do is have another state where you default construct a thread, and then once you pass it a function, you start running the function. Here, what I do is I use a lambda to wrap the given function and type erase it to a different signature. Basically, the threading library we're dealing with, the CMSys threading abstraction, it requires you to start threads with a function signature of void const star or const void star, depending on where you like to put the const, which means you can't modify the arguments, which is pretty important here. And type erasure makes me sad, but this is just a requisite for working with this library. So pretty straightforward. You recast your thread argument. You if it was null, you do something which might be through an exception, but also right now it's just terminate. You call a function, and then you signal to any threads that were waiting on you to stop. And so unlike POSIX, where you can, or pthreads, where you can interrupt threads using like a particular predefined signal, I actually define a custom signal up here. So when you call join on a thread object, what you're doing is you have a handle to another thread, and you block until the thread represented by that handle is done. So the thread handle that you have has a storage for the IDs of all the other threads that you're waiting on. So to implement join, we want to check first that we weren't already signaled to terminate, because if you block after a signal has been sent, then you will probably just block forever because you've missed the signal. You notify the thread handle that you are blocking, and then you wait forever on that thread ID to the other thread of control to send a signal to you. In a more complex situation, in something that's not just like a canned example, I would probably have more logic to handle timeouts. So rather than actually waiting forever, I would wait for a fixed amount of time and then do something after a timeout. But this is a minimal example. You might also want to handle other signals, but it's an application-oriented thing. And that's it. I think, again, this is a naive implementation, but I think join is not that hard to implement. And our implementation did introduce some overhead. So I basically compared, we can pull up another thing that I forgot to. Uh-oh. This is going to be great. You can see all the monolithic directory structures that went into this. Yeah, okay, great. So this is a canned C example that was, again, this is like showing the, an example of the C-style CMSys API. Yeah, okay. And then the kind of cleaner C++, modern C++ style implementation of it. So as you can see here, the callbacks or the thread functions are provided basically without in order to bind arguments to this, you would have to define global variables. Oh no, you would pass arguments when you call the OS thread create macro, but again, there's more kind of type erasure and casting involved to pass arguments around. So that's what I'm benchmarking, and there is overhead in the C++ wrapper. But that overhead is kind of expected because we've added, obviously we've added runtime logic to handle the thread signaling. The point I'm trying to make here is that join is not hard to implement, but I can still see why the thread abstraction was left out. Obviously because the compiler implementing libc++ doesn't want to impose a threading paradigm or an RTOS library on the users who don't want an OS. So then the RTOS implementers would have to provide an implementation of thread, mutex, condition variable, etc. But they usually don't. In fact, they usually don't have much C++ support, and that's kind of rough. Because these are nice abstractions that we'd like to be made available to everyone. And I'm seeing into the future here, seeing that the networking TS depends on threading abstractions. And so because I know that, I already feel as if, or have a feeling that the networking TS will not be provided by the maintainers of ARM, no ABI, lib C++, and that makes me sad because really what makes innovation and technology move forward faster is if people have nice to use abstractions in their hands that are fun to use and powerful, and there's a bit more overhead that goes into wrapping all this really huge variety of libraries that are available to us. But the point of finding the abstractions in the right place is that we eventually get rid of more overhead that the users have to do. And as I kind of wrote here, the text on this slide I find really important that, and I think this is a really important distinction between desktop and embedded development, is that the compiler is kind of like tightly coupled to system calls in a lot of places in the C++ standard. And system calls, I mean operating system API. And on embedded, that's intentionally a really loose connection or no connection at all. And I think kind of the language designers or standards designers have to think carefully about that relationship. And to me as a user, I'm not really sure if that was kind of thought all the way through. But again, I'm a user and not a maker of these standards, so who knows? So another point I kind of wanted to make about my adventures writing this library is that one thing about the specification for this protocol is that it's very object-oriented. And by that I mean the language describes objects, hierarchies, or kind of UML diagrams between objects, and it provides this API that kind of looks like Java and says, you know, let's say you have a custom publisher that publishes type foo. Well, you're obviously going to call it foo publisher, rather than saying you have a concept or you have a template. You have some generic thing that acts on data in this particular way. And I kind of think that in order to make these standards and protocols easier to write, then people have to take a different design paradigm. What I find interesting about DDS is that there's some places in the spec with like C++ specific language and some places with Java specific language, and then it's kind of like, well, if you're going to give me a code example, why don't give me a full code example, then actually give me pseudocode. But again, this is kind of all out of scope, and if you have thoughts on this, then totally hit me up after this. I kind of already made this point, but this was a really fun undertaking for me. I'm technically actually a hobbyist on this project right now. It's not my day job, but I really strongly believe that if we're going to make C++ on embedded happen, because this is like the year of C++ on embedded, kind of like, you know, desktop on Linux, I don't know. If we're going to make that happen, then we need better libraries, and we need good libraries to keep in mind the limitations that embedded system developers have. I want to be able to use serial for serialization without exceptions in RTTI. I want to be able to use a lot of Boost libraries without the kind of weird design gaps that taking out those parts of the language introduces. But yeah. Questions? Jeff.
So do you know about C++'s spec for freestanding implementations? I think it does kind of what you want, but nobody actually does it, maybe?
I've never heard of that.
Okay, so there's a section in the standard that's freestanding implementations, and it says you must have these things, and the rest you do whatever you want. And so not having threads is kind of part of that, right? So you don't need to have threads, you can have it if you want. And I think the goal was to do things for like that type of system. But whether it's useful or not is a separate question. I think that's useful feedback to the committee.
Yeah. And also useful because we end up spending, I think, more time talking about freestanding implementations than we need to.
Right. It's just should this new feature be in freestanding implementations, and then we kind of like, maybe, I guess.
Like the customization points for structured binaries, we spent a whole bunch of time talking about like what header can be put in because freestanding implementations.
So
you should write a paper.
To repeat that, it wasn't really a question. It was more of a point of information. Some people in the committee and the audience have pointed out there's language in the standard for freestanding implementations.
Yeah.
Okay, which I was going to ask is the difference between a freestanding implementation and a TS.
Oh, no, it's hosted versus freestanding.
Hosted versus freestanding. Okay, maybe we should talk later, but that's an interesting point. Okay, I can't read that. Okay, more questions?
Yeah, I was wondering in your Boost example, you used the map for the callbacks. Why were you doing a linear search? Are you?
Yeah, I could sort them lexicographically and then do a binary search.
If it's a Boost map, you can directly access the value of the map by using operated brackets.
Can the keys be runtime determined?
Okay, so
non-const types? Yeah.
Not really. Maybe you can use Boost find it with the mentioning lambda.
Okay. Over there.
Just an observation that a lot of luggage problem that
The
embedding
extra luggage.
gets actually, I think, mirrors into a lot of different portions. Certainly for us in finance, it's the problem is there, even though we're the furthest thing from resource constrained.
So when you say extra luggage, you mean code size or just general resources or
Just general resources. Code size,
Okay.
we're not really worried about, but we're certainly worried about the runtime effects of the extra bits and pieces.
Okay.
Why do you say that this is the embedded year for C++?
Oh, this is most. He asked, why did I say this is the year of C++ on embedded? I mostly wanted to make the Linux on desktop joke, but seriously, I think this is like set by the CppCon organizers, one of whom is in the room. Decided to have a keynote from Dan Sachs, who is also in this room. Hi, thanks for coming. And a plenary session by Jason, who was writing code for the Commodore 64, which is essentially in the class of some of the tinier embedded devices you can have. So yeah, I'm just observing that there's like this agenda that the conference organizers are pushing. I don't know. Yes, Bryce?
So there are communities that use C++, but that are generally not don't participate in the rest of the C++ community as a whole. And so one of the things this conference tries to do is bring those communities into the fold. So we've done a pretty good job of that on the game. I think we have a community who come here. And so this year we selected some keynotes that were intended to try to attract people from the embedded community. And so we'll see.
Let's take more questions. Thanks. Jens. Yeah, I would have to bench. He asked, have I considered using Brigand, which is another TMP library? Yeah, I would have to do some benchmark comparisons. So like Louis put out those comparisons of different TMP libraries. First of all, I would have to check that which ones provide the functionality that I need for patterns that I actually want to keep. Because we showed that at least one pattern I was interested in was not as good as yeah. And then I would actually have to do like code size analysis because I think his benchmarks are just compile time analysis. So, other questions? You? Okay. Well, we're a bit early. Thanks.